So if we consider it that way, then X transpose X transpose Ax vector plus A multiplied by X vector, the whole transpose, multiplied by vector. Okay, can you identify how we have applied this rule? So this is equal to X transpose, and by this rule, dou by dou x bar of X transpose into A is A transpose, the one above it. Dou by dou x of A into X is A. So X transpose multiplied by A plus, now transpose of this is X transpose multiplied by A transpose. Okay, by the properties that we had seen in the previous lecture. Now, although I have not stated this rule, but dou x bar by, like, the partial derivative of x bar with itself gives an identity matrix I. Okay, I'll just write it here. Dou, actually dou x bar by dou x bar is nothing but, we can say dx bar by, because there is only one variable, and it is equal to I. Now this I is of the dimensions. So if x vector is of the dimensions n cross 1, then this will be of the dimensions n cross n. But this is an identity matrix. So we'll have identity matrix here. We'll have I over here due to this operation, which gives us nothing but X transpose plus A transpose. Now, uh, taking X transpose common, you can write this as A plus A transpose. Okay. So the derivative of this is the final answer. No more simplification possible at this stage. Now this value may depend on properties of A as a matrix, but as such, this is the most simplified form that we get using the properties. And now if we substitute the values, let's say we have, okay, let's take an example. So for example, f of xy, f of xy is equal to xy multiplied by, any numbers, multiplied by xy. Okay. If we apply this property, derivative will be 4x plus 5y, 5x plus 15y. Now if we would have calculated without using this property, how it would have looked like. So f of xy, if we simplify using this, just to cross verify, or without this property, if we would have done, it would be uh, 2x plus y and 4x plus 7y multiplied by xy, which is 2x square plus xy plus 4xy plus 7y square, which is 2x square plus 5xy plus 7y square. Now if you calculate the gradient of this, uh, not gradient actually, just the partial derivative, dou f by the gradient actually, yes, gradient of f will be 4x plus 5y when you differentiate with respect to x, and 5x plus 14y when you differentiate with respect to y. Okay, any questions, any doubts up to this point? Ask your doubts, please. Okay, no questions, then I'll proceed. So, okay, now gradient of vectors with respect to matrices. So consider this example, gradient of vectors with respect to matrices. So F is equal to A into X vector. Now in this case, let's say A is a M cross N matrix, and X is an N cross 1 vector. So when you multiply these, you get the dimensions of F will be M cross 1. That is, in short, M cross 1 r gets to M. Dimensions will be M cross 1. Now till now, so previously we found a derivative of F with respect to x, that is dou f by dou x. Now let's find the derivative of this with respect to A. Okay, so now dou f by dou A, so to calculate dou f by dou A, we'll first have to write this down as, so fi, components of f is a vector function, so components of fi, ith component is equal to summation j goes from 1 to n a I j into xj, xj, or I goes from 1 to n. Okay, this is like matrix multiplication. Okay, so again partial derivative will have to be calculated. Now till now we have learned how to calculate partial derivative with respect to a vector. Okay, so let's say dou fi by, with respect to a row of a, a row of a. Okay, so now these are the rules for this for these partial derivatives. So if you are calculating the partial derivative of fi with respect to a row of a, and if the function number and the row number is the same, that is dou fi by dou ai colon, this means ith row and all columns. This colon means all columns of the ith row. Basically it means the ith row. Okay, so dou fi by dou ai colon, which means the derivative of fi, partial derivative of fi with respect to the ith row of a, it is the same as x transpose, x transpose. Okay, and in case the row number is different, in case the row number is different, so dou fi by dou a k not equal to I. So for all other rows other than the row number I and any column, all columns. So that's why colon a k comma colon and k not equal to I. Then this is given by the zero vector. And why transpose? Because these are all considered column vectors, whereas in our answer, these have to be taken as row vectors. That's why we are taking the transpose. Okay. So likewise, if we stack these partial derivatives together, it gives us, and write it below, it gives us dou fi by dou a is equal to first row 0, second row, third row, up to the I minus first row will be a 0. Ith one will be x transpose, and then again from I plus 1 to row. How many f's are there here? 1 to m. So up to the mth row will also be 0. Okay. And now these will be stacked together as, ultimately what we want was dou f by dou a. This will be the gradient of f with respect to a, and this will be dou f1 by dou a to dou f m by dou a. Okay, I'll just revise these steps once again, how we derived this. So first we had f is equal to a matrix multiplied by vector x bar. Dimensions of a are m cross n. Dimensions of the vectors are n cross 1. Therefore, dimensions of f are m cross 1. Then to differentiate f, to find the gradient of f, we first have to find the partial derivatives. So partial derivative for, and f is a vector function, so it will have components fi. It will have m components. Okay, m component functions. Each component is a function. So for each function, now we have to find the partial derivative of each function with respect to the matrix A. But again, this has to be broken down into finding the partial derivative of each function with respect to each row of the matrix. Now these are the two rules for finding partial derivative of fi with respect to rows of matrix A. If the row number is I for the function fi, so for example, if we have f3 and row number is also 3, then the row number is also 3, fi and ai match, then the answer will be X transpose. And if the row number is other than I, then the row will be a row of zeros. Okay. Now,
Hello, sir.
yes,
Sir, why we are calculating the derivatives with respect to a?
because in the previous lecture we already for the same expression we already calculated with respect to x. So now we are trying to calculate with respect to a. Here we had calculated derivative of ax with respect to x. Now we are calculating with respect to a, the other possible thing with it. Okay.
Okay, sir.
Okay. Now we have found all the partial derivatives. Okay. So finally the gradient of f with respect to a will be combining all these partial derivatives basically. Okay. So partial derivative of f1 with respect to a, partial derivative of f2 with respect to a, up to partial derivative of fm with respect to a. Okay. Any questions, any doubts at this point? Yes. Okay. Mm. Let's try for the same example as above. Okay, okay, someone has asked something in the chat. I heard. Gradient will be a matrix. Actually, okay. So I think I have to introduce the concept of tensors over here. Okay, let's try to solve this one first. same matrix. Let's take f of xy is this system. So now we want to find derivative of, so here fi is to this row basically 2 4, that is, see, let's follow these steps. So fi, by the formula, repeat the formula here. Fi is summation j goes from 1 to n aij into xj, I goes from 1 to n. And in this case, A is 2 cross 2. So basically m and n are both 2. In this case, A is 2 cross 2, x is r square, and f is also r square. Okay. So first, if I is the multiplication of this, so f1 is 2x plus 4y. F1 is a function of x and y, which is 2x plus 4y, and f2 is also a function of x and y, which is x plus 7y. Okay. Now dou f1 by dou a1 will be x transpose, which is x1, and dou f2 by dou a2 will be xy. The other two, that is, the other two, I mean dou f1 by dou a2 will be 0 transpose, and dou f2 by dou a1 will also be 0 transpose. Now how do we collect these things basically? Okay. So overall, dou f1 by dou f1 by dou a is the collection of uh, so these two basically, that is xy and 0 0 and dou f2 by dou a will be 0 0 and x bar. Okay, and the combined final answer, that is the gradient of f with respect to a will be these two above one another. So it will be how. So this is basically we are moving into the domain of tensors, which after writing this I'll just explain in short what do you mean by a tensor. Okay, I'll keep all the braces as it is while stacking this and not to omit anything. So just writing these one below the other, some brackets. These brackets can actually be some brackets can actually be ignored in this case without any causing any trouble to the meaning or the, without changing the final answer, that is. Okay, so this is how its derivative looks like. Now answer still has x y x y because we are not finding gradient at any particular point. So in the question, if we are asked to find gradient at a particular point, this will how it will look, and this is the working behind it. Okay, so what do you mean by a tensor? Okay, I'll go to that. Any questions in this working of in this answer that we just found? Any questions? No questions? Okay, so can you explain how we got d dou f1 by dou a1? Okay, dou f1 by dou a1. Now I'm not proving this to you, like why is it, but this is the property that the partial derivative of f1 with respect to the first row is equal to x transpose, and partial derivative of f2 with respect to the second row is equal to x transpose. And whenever the row number and column number do not match, then it is um, 0 transpose. Okay. Okay, so let's see the concepts of scalars, vectors, and tensors. Like concept of tensors basically. Actually, actually speaking, so okay, so what do you mean by a scalar? Scalar is any number, let's say 1. Vector mathematically looks like this. Matrix looks like this. And we always have downwards compatibility. So for example, when saying when defining matrices, we can say also after defining matrices we can say that vector is also kind of a matrix, but it's like a row vector or a column vector. Okay, similarly we can say scalar is nothing but a 1 cross 1 matrix. Okay, That also we can say a 1 cross 1 matrix is nothing but a scalar. Now, tensor looks like this. It's a four-dimensional entity. Okay, it's a four-dimensional entity. It's a four-dimensional entity. And after defining tensors, we can say that all of these that we studied earlier are in fact tensors. So, uh, scalar is a zero-dimensional tensor. Vector is a one-dimensional tensor. Matrix is a two-dimensional tensor. And tensor is a tensor. Like it's a four-dimensional. We don't do not have any uh, higher. It's a three-dimensional tensor basically, not four-dimensional. Sorry, it's a three-dimensional tensor. Okay, three-dimensional, and anything beyond this will also be called as four-dimensional, five-dimensional, because we do not have any specific names for a three-dimensional tensor or a four-dimensional tensor. So all of them are just tensors. Okay. So is this concept clear? So our answer, our gradient is actually a tensor. Okay. But for all practical purposes, we can skip some of the braces and it will look like a matrix. Even this looks like a matrix only, but this is actually a tensor. Okay. Any questions? Okay, then I'll proceed to differentiation of, which is quite more complicated. Differentiation of matrices with respect to matrices. Okay. So gradient of matrices with respect to matrices. Okay, now this is actually quite complicated, and this so there will be no examples or questions to solve based on this particular section. So we'll consider a very specific kind of product of matrices. Let's say R transpose multiplied by R, where both like where R is a square matrix. Uh, or okay, we can have R as a rectangular matrix as well. Okay, let's say R is any general matrix and R transpose multiplied by R. Okay, so let's say K is equal to R transpose multiplied by R. Dimensions of R are M cross N, and dimensions of its product K will be, what will be the dimensions of K? N cross N is correct because we are multiplying with transpose first. R transpose multiplied by R. So R transpose dimensions will be N cross N, and dimensions of R are M cross N. Therefore, the result will be N cross N. Okay. So dimensions of K will be N cross N. Okay. Now let's try to calculate the derivative of the gradient of K with respect to R. Okay, so for that, okay, I think I'll directly. Okay, so okay, fine. The gradient will definitely be a tensor. Okay, so the gradient of k respect to r will be, will have the dimensions of n cross n cross m cross n. That is, each cell each cell will be of the dimensions n cross n, and the total number of cells, if you arrange as a matrix, it will be m cross n. Okay, for okay, now if you try to differentiate any particular uh, any particular entry of k with respect to r, so kpq first of all is going by the basics of matrix multiplication, it is the dot product of pth row transpose of the, so kpq is given by uh, small r. I'm indicating the because okay, so this is the pth column of r, not r transpose, pth column of r, which becomes the pth row of r transpose, qth column of r, which is equal to summation m goes from 1 to m r m p into r m q. These are just two elements, scalars, two elements, nothing but the dot product. Do you get this point? Okay, so if we calculate the derivative of with respect to r, ij, this will be summation m goes from 1 to m
Excuse me, sir.
yes.
Sir, can you repeat the notations once again?
Okay, k is the product of r transpose with r, so I should have, okay, I should have renamed this as A or something, but let's say R is the name of the matrix and this R means the real numbers. So the dimensions of R are m cross n, and therefore the dimensions of product, because we are taking R transpose first and then R, dimensions of the product will be n cross n. Okay, so this is the final thing. So this is the gradient of the product K. Okay, gradient of the product K, and we can actually omit this part, but it is with respect to R. This can actually be omitted, but this is with respect to R, just to indicate that here we are calculating with respect to a matrix. That's why I had written R over here. Then its dimensions will be n cross n into m cross n, which means there will be, so if you write it on a paper, it will be an m cross n matrix, but instead of each element you will have an n cross n. um, I called it as a cell basically. So each element will actually be a matrix of dimensions n cross n. Okay, so this is this. Then kpq means, again this is just the matrix multiplication rule which I'm stating again. So when I'm multiplying R transpose with R, I'm multiplying the row of R with a column of R, right? Row with column, row with column. That's how we multiply. We find, and this is like finding a dot product. Okay, so kpq means pth row of R into qth column of R. But because this is R only, R transpose multiplied by R, so it is pth row of R transpose is nothing but the pth column of R. So that's why I wrote Rp transpose, which means the transpose of the pth column of R is the pth row of R transpose. So Rp transpose, which is a row vector, multiplied by Rq, which is a column vector, pth row multiplied by rth column will give me kpq. Okay, and internally the multiplication will look like this. First row, because there are, the dimensions are m cross n, so going from first row to the mth row, first row to the mth row, multiply every individual, uh, not row, what I mean to say is, so you will take a row of R transpose. So okay, it has, R transpose actually has m rows and n columns. R has, and R transpose will have m columns and n rows. Okay, so I'm I'm multiplying R transpose with R. Okay, so let me rewrite this. R transpose multiplied by R, this will have n rows and m columns, and this will have m rows and n columns. Okay, so m equal to 1 to m, multiply R m p with R m q from this one, and thus you will find kpq. And now derivative of kpq, partial derivative of kpq with respect to rij. Now rij is just one element that we are finding a derivative with respect to. Okay, So we are finding derivative of one element of the product KPQ with respect to one element of R, that is Rij. Okay, is the notation clear or any questions? No example for this. Example as in, because there will be no questions on this to solve as such. I'm just explaining it as a theory, like, because it will be too complicated to solve this. Okay, so let's denote this as a partial derivative PQij. Okay, PQij. So delta of PQij will be equal to Riq if j is equal to p and p is not equal to q. Rip if j is equal to q and p not equal to q. 2Riq 2Riq if j is equal to p and p is equal to q, and it will be 0 otherwise. Okay, now p, q, j. P, q are the dimensions of k. Okay? P, q are the dimensions of k. So p, q vary from 1 to n, obviously, because the dimensions of k are n cross n. Ij, which are the dimensions of uh, R. So I varies from 1 to m, number of rows in R, and J varies from 1 to n, which are nothing but the number of columns in R. Okay, so how many elements? So how many possibilities will be there in this case? Okay, so let's take again the same example. If I took of a 2 cross 2 matrix, okay, that is m equal to 2 and n equal to 2, then the product will have, this is your final answer, this is our final answer that we have reached, final answer. So delta of PQij will be, like, how many will have to calculate. Basically dimensions will be, so 2 into 2 into 2 into 2, which is 16. You'll have to calculate 16 such elements. Okay, and the so it will look like this. Okay, 2 by 2, 2 by 2, 2 by 2, 2 by 2. In fact, because now the time is up, but actually in, uh, in the next lecture or in the tutorial, okay, will you be able? Okay, so are you able? wait for some more time. We can solve for one matrix if you are ready to wait for some time. No answers? Okay. I'll take the attendance. See, for 2 cross 2, the answer will look like a 4 cross 4 matrix, but it is actually a tensor 2 cross 2 matrix, and each element is a 2 cross 2. Okay, so okay, I'll just solve it for one matrix. So let's take the same matrix 2 4 1 7. Okay, if R is 2 4 1 7, R transpose is 2 4 1 7, and K is, let's say, R transpose multiplied by R, then the gradient of K with respect to R will be, you'll have to calculate the 16 elements. So PQIJ, all of them range, all of them have possible values 1 2. Okay, and so let's consider when all of them are 1, P1 Q1 I1 J1. So J is equal to P and P is equal to Q. Then it is 2 I Q. Okay, let's calculate during next lecture itself, I think. Okay, it will take time. It will take time to explain. Okay, so I'll take the attendance now and we'll stop for now. Bharat.